Okay, so here it says that we should determine the de Broglie wavelength of a 3.17 electron volt electron. So the equation for the de Broglie wavelength is going to be lambda is equal to h over p, and p is equal to mass times velocity. P is the momentum here. Now k is equal to half mv squared. If I were to multiply the top and the bottom by m, I would get the following. I'll get ke is equal to half m squared v squared over m. Now p is equal to mass times velocity. So k is equal to half p squared over m. Now let's do some simple cross multiplication. We'll get p squared is equal to times m times ke. So essentially, p is equal to the square root of 2 times m times ke. Okay. Now I'm going to come back here to the equation. So h over 2 times m times ke. Okay. Now, since mass is in kilograms, if you look at the equation sheet, then because the mass is in kilograms, right, which is this one here, then for the h, we have to be using the 1 in joules second. Okay. And the ke has to be changed from ev, which it currently is, to joules. Okay, so to change the EV to joules, you must multiply it by 1.6 times 10 to the power of negative 19. Now let's get to work. So now we're going to have H, which is 6.63 times 10 to the power of negative 34 over 2 times the mass, which is 9.11 times 10 to the power of negative 31 times the KE, which is 3.70, but like I said, you must make it in 2 joules. Let's see how much we will get in the calculator. I got myself now 6.38 times 10 to the power of negative 10 meters. Okay, that was part A. Let's now move on to part B. So in part B, it says that we have 3.8 TeV for the energy of the electron, and we want to find the wavelength. So I'm going to say E is equal to H times F. So E is equal to hc over lambda. So lambda is the wavelength, which equals to hc over E. Now, if you look at the equation sheet, you will see that hc, okay, is basically given to you in joule times meter or eV times nanometer. And since the energy is in electron volts, I'm going to go with the 1240 electron volt times nanometer, I mean. So we're going to say 1240 over 3.70, and let's get the wavelength. And I got myself 335. Unit is going to be nanometer. Okay, let's move on to part C now. So in part C, it says that experiments reveal that 2 additional wavelengths are emitted if the beam of energy is raised to at least 4.90 electron volt. Let me address something now. So basically for 2 wavelengths, so for the wavelength to be emitted, then the electron has to drop to a lower energy level. So right now we have 3 energy levels, okay? They're as such. N is equal to 1, the ground state, which stands at 0 electron volts. N is equal to 2, the first excited state, which stands at 3.70 eV. N is equal to 3, the second excited state, or the third energy level, which stands at 4.90 eV. Okay? So now, for the electron to drop, it has to go down, right? So that's the first drop, that's the second drop, and that's the third drop. We're going to call the drop from the N3 to the N2 E2. Actually, let's call that something else. Let's start with the N2 to N1. Let's call that E1 because it's the drop from the first excited state to the ground state. Let's call N3 to N1 E2. It's the drop from the second excited state to the ground state. And let's call the drop from N3 to N2 E3. Okay. And now let's find their values. So now E2 is equal to 4.90 minus 0, 4.90 EV. E3 is equal to 4.90 minus 3.70, 1.20 EV. And E1 is equal to 3.70 minus 0, which is 3.70 EV. So here we have our three possible energy states, okay, for the electron as it drops from a higher energy level to a lower energy level.